All right, students, let me try another video solution here. This is chapter 5, number 18, but it's from the conceptual one because there's an 18 on the exercise, which I already sent you the video solution. But this is the conceptual one. And this one is, I can see this one could be a little tricky. You need material from chapter 4 and chapter 5. And anytime that you have a problem that kind of incorporates not only this chapter but last chapter, it gets a little harder here. So let me just kind of remind you of what we're doing in this chapter. So chapter 5, we have this universal law of gravity, okay? And we're looking at, say, two objects of mass 1 and 2 separated by a distance of r, and then there would be this force between them. And so Newton figures out this little formula. He doesn't really explain why there is a force of gravity, but at least he figures out that the mathematical pattern to the force of gravity, and that it's universal, that it's just any two objects. Now, back in chapter 4, we did a lot of net force stuff. Net force was really the sum of all the forces. If I can use kind of a math symbol here, this is that capital sigma. And so maybe if we say I equals 1 to n, we could say in kind of math symbols that if you add up all the forces, and remember they have a direction to them, that's why we've been working with not only magnitude and units, but also direction, you would get the net force. And that has to equal to ma. And so we would always want to combine all the forces together. Now, I think for simplicity, given that this is an introductory to physics course, we really kind of just give you guys two forces. And really, it's the combination. And it's probably best described as a combination, not a summation, because summation almost sounds like you add. And you don't. You got to look at their directions. And so if you have one force going to the right, but you have another one going to the left, you would subtract those to get to the net force. Now, if they're in the same direction, and so they look something like that, right and right, you would add them. And, of course, if they were perpendicular to each other, we would do the Pythagorean theorem. If they were off at some other angle between them, maybe 120 degrees, the result we can draw, and that's the lab we did on vectors. A little bit harder to do the math behind there. That involves some trigonometry. So we're kind of staying away from those kind of problems in this course. You'll see them in the next course because that's kind of the difference between this intro course 102 and the next one, 121, is really the level of math. And so in the next level, you're expected to do trigonometry as well as calculus. And so it's kind of a big step up in terms of the math level. But this course is designed more of the conceptual ideas as well as some basic mathematical ideas of what physics is. And so that's why we kind of stay away from these harder ones, other than drawing pictures so you can learn the conceptual idea. Okay, so keeping in mind about adding forces together from chapter 4 and keeping in mind the universal law of gravity, this is really where 18 conceptual comes in. Let me read it. You are standing on a bathroom scale in an elevator when suddenly the cable breaks and the elevator falls freely down the shaft. Now, let me just kind of make a line here and say, okay, so what would be happening at first before the cable broke? So maybe I'll draw the elevator here. And maybe here you are standing. And let me give the scale. We'll give it an oversized scale here. But if we do this free body diagram stuff that we learned back in chapter 4, okay, and we look at just the person standing in the elevator, we would see that there would be this force of gravity. So let me put force of gravity. Maybe I'll even put F sub g. But again, this is where chapter 5 comes in. It's g m1 m2 over r squared. That's what's pulling you down. Now, what's pushing you up is this contact here, the normal force. And so it would be at your feet here. Maybe I'll just draw it to the side so that I'm not kind of drawing an arrowhead on top of my person here. But there would be an upward force. This would be the normal force if I want to label it with an N or maybe an S for the scale. But that's kind of the crutch to this problem because we need to understand where the forces are coming from. And so this individual has two forces, one from the force of gravity, the other one from the contact with the scale. And we need to understand that the reading on the scale then is really this normal force. Because this problem, goes on to say, how does the reading on the scale change from just before to just after the cable breaks? So we really are asking about this force. And what this problem does, I think, really well is it helps you if you haven't kind of dissected it or differentiated between all these forces back in chapter 4 is there's three, I don't want to say there's three forces because there's only two, but then the combination of those two is the net force. All right. So this problem could ask about the force of gravity. This problem could ask about the normal force or the force from the scale, or this problem could ask about the net force. Now, there's more to this question, but what I've read so far is asking about this. So let me put it in math form. So if I did this, if I said the net force then would be equal to, and so I would have the normal force pushing up, that's the reading on the scale, and I would have the gravitational force pushing down. And these are the three questions that this problem could have asked about the force. We've got the force from the scale, we got the force from gravity, and we got the net force. Now, if I come back to the question, I'll read it again. It says, how does the reading on the scale change just before and just after the cable breaks? So they're asking about this one. They're not asking about the net force, and they're not asking about the gravitational force. Although, let me read on, and it does ask about this one. It says, how does the force of gravity that the Earth exerts on you change over this same time interval, meaning right before and right after? So they're really asking about both of these, right before and right after. They're never asking about the net force. However, it might be nice to talk about all three of these, even though they don't ask about this one, so we don't confuse them. And that is usually the common mistake in this problem, is students go ahead and answer the force from the scale as if it was the net force. And that's where they make the mistake. So I wanted to start here by kind of taking you back to chapter 4. And I guess we have a little bit of chapter 5, but we're going to get more into chapter 5 here. And just make sure we differentiate between all these forces. Okay, so with that in mind, let me point out that before the cable break, so maybe I'll put here before. Do they say standing on a bathroom scale in an elevator when suddenly this cable breaks? So I'm going to take it to mean that the elevator is, not moving at the time, just standing there on the scale, because I want to be able to say here that the net force is equal to 0. Or put another way, this is kind of how a scale normally works. You normally stand on a bathroom scale in a place where you're not moving. It's usually on the floor of the bathroom. And your net force is 0. And let me point out again, this problem did not ask about the net force. But if they had asked about the net force before the cable break, I would say it's 0. They're not asking about that one. What they are asking about are these two. And so in this case, this would tell me that the force of gravity and the force of the normal, that is the force from the scale, are the same. And, of course, the force of gravity is probably the easiest one to answer because it has to do with just what we would call the weight. This is the definition of weight. It is the force of gravity pulling you down. So the force of gravity pulling you down is your weight. So the reading on the scale would also equal your weight. That's why when people stand on a scale in a normal bathroom setting, their net force is 0, and what they do is they take the reading on the scale. So notice that the reading on the scale is not the net force. The scale doesn't say 0. The reading on the scale is the weight of the person. So to answer this two-part question, before the cable breaks, the force of gravity is the weight of the person, and the reading on the scale is also the weight of the person. Now, let's look at after. Okay, now after it breaks, there is an acceleration. In fact, I think they're trying to say here that that acceleration, that free fall, the net force then equaling ma, and we would be in free fall, so that would equal mg. And so mg then is the normal force minus the force of gravity. Now, let me emphasize, I'll just kind of rewrite this down here. But let me emphasize the force of gravity, what this chapter is all about, has to do with the masses of them and the distance. And it's the distance from center to center. So even if you just barely fell, this wouldn't really change. And so your force of gravity really is the same value. And so I would say that what this is trying to say is that your force of gravity is still the mg. Which means then if you cancel off the mg, your normal force is 0. And that makes sense. You actually have a net force. In other words, gravity is pulling you down with mg, and the scale isn't doing anything to lift up. So your net force is mg, and that's why you're falling. Sometimes we use a bad phrase when we say something like, hey, when you're free falling, you know, like jumping out of an airplane when you're skydiving, or you're on one of these fancy rides at amusement park. Free fall at Magic Mountain is an example of that. You know, you say, oh, you're weightless. And that's not a good phrase, because you're not weightless. The fact that you're falling is because you do have weight. Gravity is pulling you down. What you don't have is any support pushing you back up. Right now, you probably have that. You're sitting on a chair probably watching this video, and you're going, okay, gravity's pulling me down, but the floor that I'm sitting on, which is probably like a foundation of some kind. If you're on the first floor, maybe it's a wood, I don't want to say deck here, but the second floor of an apartment building, or third floor, whatever. But it's you know, there's some kind of a support there pushing up. I doubt if you're actually sitting on a scale, but if you're sitting on a scale, you could actually then read how much is pushing you up. And so when you break the cable, there is nothing pushing you up. And that's what this is trying to say. So the reading on the scale would be 0. The scale's not pushing anything. There's no interaction between you and the scale. All right, so to finish this problem, I would have to say then, okay, so right after the cable breaks, the reading on the scale would be 0, and the force of gravity would still be the weight. So the boring answer is the weight one, the force of gravity. The force of gravity doesn't change before and after. The force of gravity remains the same. What changes is your upward supporting force, which is coming from the scale. It was equal to your weight, and that's why you weren't falling, and then it drops to 0, and of course then that's what pulls you down. Hopefully that helped.